true motivated leaders for the students, teachers, and professors in the area of entrepreneurship through the wonderful scientific experiments. Let me give the brief introduction of Dr. Boaz Almog. Dr. Boaz Almog did his PhD from the School of Physics and Astronomy, Tel Aviv University, Israel, and whose TED Talks are numerous educational videos were watched by over 15 million viewers worldwide. Being a passionate entrepreneur, Dr. Almog invented and founded the quantum experience in 2012 and the Brixo in 2015 as an ultimate combination of the blocks. And you would surprise that Brixo raised $20 million, dollars, approximately 14 crore rupees, by delivering more than 12,000 kits to the customer in the top organizations like NASA, Harvard, MIT, Stanford, Max Planck Institute, and many more. He is holding 7 patents in the area of smart toys, superconductivity, and circuits building systems. Dear friends, without delaying it further, with all due respect, let me welcome our today's eminent speaker and scientist, Dr. Boaz Almog, known to be very great inventor. And dear sir, you are heartily welcome amongst the future aspirants. Now, before I hand over the session to you, I would like to share a short 10-minute video, TED video here. And after that, I request Dr. Boaz Almog, you just initiate your session. Thank you. I'm sharing your video right now.
The phenomenon you saw here for a brief moment is called quantum levitation and quantum locking. And the object that was levitating here is called a superconductor. Superconductivity is a quantum state of the matter, and it occurs only below a certain critical temperature. Now, it's quite an old phenomenon. It was discovered 100 years ago. However, only recently, due to several technological advancements, we are now able to demonstrate to you quantum levitation and quantum locking. So, a superconductor is defined by two properties. The first is zero electrical resistance, and the second is the expulsion of magnetic field from the interior of the superconductor. That sounds complicated, right? But what is electrical resistance? So, electricity is the flow of electrons inside the material. And these electrons, while flowing, they collide with the atoms. And in these collisions, they lose a certain amount of energy. And they dissipate this energy in the form of heat. And you know that effect. However, inside a superconductor, there are no collisions. So there is no energy dissipation. It's quite remarkable. Think about it. In classical physics, there is always some friction, some energy loss, but not here, because it is a quantum effect. But that's not all, because superconductors don't like magnetic fields. So a superconductor will try to expel magnetic fields from the inside. And it has the means to do that by circulating currents. Now, the combination of both effects, the expulsion of magnetic field and zero electrical resistance, is exactly a superconductor. But the picture isn't always perfect, as we all know, and sometimes strands of magnetic field remain inside the superconductor. Now, under proper conditions, which we have here, these strands of magnetic field can be trapped inside the superconductor. And these strands of magnetic field inside the superconductor, they come in discrete quantities. Why? Because it is a quantum phenomena, it's quantum physics. And it turns out that they behave like quantum particles. In this movie here, you can see how they flow one by one discretely. This is strands of magnetic field. These are not particles, but they behave like particles. So this is why we call this effect quantum levitation and quantum locking. But what happens to the superconductor when we put it inside a magnetic field? Well, first there are strands of magnetic field left inside, but now the superconductor doesn't like them moving around because their movement dissipates energy, which breaks the superconductivity state. So what it actually does, it locks these strands, which are called fluxons, and it locks these fluxons in place. And by doing that, what it actually does is locking itself in place. Why? Because any movement of the superconductor will change their place, will change their configuration. So we get quantum locking. And let me show you how this works. I have here a superconductor, which I wrapped up so it stays cold long enough. And when I place it on top of a regular magnet, it just stays locked in midair. Now, this is not just levitation, it's not just repulsion. I can rearrange the fluxons and it will be locked in this new configuration, like this, or move it slightly to the right or to the left. So this is quantum locking, actually locking, three-dimensional locking of the superconductor. Now, of course, I can turn it upside down and it will remain locked. Now that we understand that this levitation, so-called levitation, is actually locking, yeah, we understand that. You won't be surprised to hear that if I take this circular magnet, in which the magnetic field is the same all around, the superconductor will be able to freely rotate around the axis of the magnet. Why? Because as long as it rotates, the locking is maintained. You see, I can adjust and I can rotate the superconductor. We have frictionless motion. It is still levitating, but can move freely all around. So we have quantum locking and we can levitate it on top of this magnet. But how many fluxons, how many magnetic strands are there in a single disk like this? Well, we can calculate it, and it turns out quite a lot. 100 billion strands of magnetic field inside this 3-inch disk. But that's not the amazing part yet, because there is something I haven't told you yet. And and the amazing part is that this superconductor that you see here is only half a micron thick. It's extremely thin. And this extremely thin layer is able to levitate more than 70,000 times its own weight. It's a remarkable effect. It's very strong. Now, I can extend this circular magnet and make whatever track I want. For example, I can make a large circular rail here. And when I place the superconducting disk on top of this rail, it moves freely.
Dr. Boaz, can you see the video?
And again, that's not all. I can adjust its position like this and rotate, and it freely moves in this new position. And I can even try a new thing. Let's try it for the first time. I can take this disk and put it here. And while it stays here, don't move, I will try to rotate the track. And hopefully, if I did it correctly, it stays suspended. You see, it's quantum locking, not levitation. Now, while I'll let it circulate for a little more, let me tell you.
Dr. Boaz, we just wait. I think some technical issue is there for the YouTube policy. I am just sharing again for a while. For a only last main portion I will share. Just a wait. Stop sharing and then I'm sharing again. It was. I'm sharing the screen. વાંધો નહીં થઈ જશે. We just okay.
Maybe I can take it from here, Dr. Abe.
Dr. Boaz, you can start the session now. Later on, I will
Okay.
share your video. Okay.
Yeah, that's okay. So, first of all, I'm excited to speak to you and excited to be here. And thank you, Dr. Abe, for the very, very warm introduction. I hope that next year or sometime in the future, I will be able to visit you physically.
Yes.
And show you some of the things that we are working on. And as you see in a minute, things are changing in the scientific community. And my goal is to take all the great science and make it as much as accessible as possible for students, for everyone. So first of all, thank you. I'm excited, really excited to be here. So let me share my screen. I'll show you something that I prepared, and I also have here a few demonstrations.
Yes.
So let's start.
Boaz, before we start, let me check with my team whether this is broadcasting or not. Let me give you 1 minute only.
Sure.
ચલો એ જવા દો આપણો ગૂગલ મીટ વાળું લાઈવ કરતો ને ચલો વાંધો નહીં ભલે એ જવા દો પણ સાહેબ એવા તૈયાર થઈ ગયા છે તો તમે એક વખત શેર કરી દો ને ફટાફટ ગૂગલની આપણી લિંક જે છે ને ગૂગલ મીટ વાળી જે ડિસ્કશન છે ને એ શેર કરો તો હવે અત્યારે પ્રેઝન્ટ કરશે એ સર you can start the session now. We are live on channel.
Okay,
Thank you.
great. So if there is any problem or if you have any question, really feel free to jump in and ask. I know it's difficult in these virtual presentations, but let's try to make it as much as possible front lecture or something like a discussion. So
we have just anyhow managed. Yes.
So I wanted to talk to you about two things. First is superconductivity and how we take superconductivity and put it in the hands of students, of the general public. And later, if you allow me, I will show you a little bit about the second project I did, which is bringing building blocks of electricity, building machine, building crazy machine, and if I have a few minutes, I'll show you
Sure.
what it does. But first, let me just say that about superconductivity, and I hope most of you heard about superconductors before today. And the reason is superconductors are quite an old phenomena. Let me show. I put my face here, so maybe it will be easier. So superconductors are an old phenomena, right? They've been discovered over 100 years ago by a Dutch physicist, and at the time they researched how certain materials behave when you lower their temperature, and they debated whether certain materials will have zero electrical resistance or higher electrical resistance as you go down. And at that time, they managed to reach lower and lower temperatures. Today we can use liquid nitrogen, right? Liquid nitrogen minus 200 degrees. When you take nitrogen gas and liquefy it, then we get to lower temperature. But 100 years ago, it was not trivial. And what commonly on us, the Dutch physicists discovered is that it took certain metals, in this case maybe tin and lead, and when it measured the resistance to electrical current, suddenly at a certain temperature it drops to zero. And this is super amazing and surprising, because what it means is that this material loses its resistance and its energy loss. Right? When everything we do around here, around the classical world that we live in, has some energy loss, some friction. Like when a car is moving, it loses some of its energy to friction, to heat. When you do some work, right? A machine does some work, it loses some of its energy to heat. But here we have a machine, we drive current, and suddenly the current doesn't lose its energy, so it can go perpetually forever. And it was quite surprising. And since then, since 1911, we've been trying to catch up and find new materials that will be able to drive currents, electrical currents, without any friction, without any energy loss. And this will change history. And I prepared this diagram to show you how this search for new material advances. And right now, you see in this graph the temperature, the transition temperature for superconductors as a function of the year. And you see that it started very, very low at around zero temperature, 0 Kelvin, or approximately minus 273 degrees Celsius, which is the lower temperature possible. And it increased until gradually until in 1986, two physicists discovered a new family of materials that can suddenly become superconductors using only liquid nitrogen. Liquid nitrogen is super easy to create. It's super affordable. I'll show you a few experiments with just liquid nitrogen, super cheap. You can demonstrate this at any classroom, at any birthday. You can make ice cream with liquid nitrogen. So it suddenly became available. And for since '86, it's been like almost 40 years, the superconductors have been stuck in liquid nitrogen temperature. Of course, there have been some advances at exotic superconductors like mercury-based superconductors, but most of the superconductors were stuck here using liquid nitrogen. And just a week ago, we found out that a new family of materials, a new type of materials have been discovered that is superconducting at room temperature. Now, this is a revolution, because if you have superconductivity at room temperature, you can develop new devices that operate without losing energy. You can store energy, you can levitate trains, you can do MRI machines. Now that we know that there's a new family of materials that superconduct at room temperature, of course, these materials are not perfect yet. They need a lot of pressure, like 20 million atmospheres, I think, something like that. 4 or 6 or 10 gigapascals. It's huge pressure. So right now they need diamond anvil to pressure these materials. You see it here on this picture in the center. You see how they compress the superconductors, and then the superconductor becomes superconducting to temperature. But 10 years from now, 20 years from now, we will be able to find variants on these materials that will superconduct at room temperature. Now, remember this, and remember what I'm going to show you with the current superconductors, the superconductors that need liquid nitrogen. Now, this is what we have today at the lab. It's a complex superconductor, very, very complex. It needs layers, two-dimensional layers of metal oxide. In this case, it's copper oxygen. Copper, it's a very common metal, of course. Barium oxygen and yttrium. These are relatively easy to procure metals, but we need to construct a very, very specific material. And this material specifically is called YBCO, yttrium, barium, copper, oxygen. And a lot of effort is done how to prepare this material, and any changes with the preparation harms the superconducting properties. So it's quite difficult. Here you can see a scanning electron microscope of this material. And what I want you to remember from this picture is the fact that although it's a almost perfect crystal, there's a lot of imperfections. You can see all these boundaries and surfaces and grains all across the material. And it turns out that this imperfection is critical to the levitation that you saw previously in the film. And I will say a few words about it in a few minutes. So one of the basic properties of superconductors is the fact that they don't like magnetic fields, and it's called the Meissner effect. It's one of the properties that define what a superconductor is. And the famous experiment when you take a superconductor, you put it in a magnetic field, and it expels the magnetic field by the only means possible for the superconductor, which is driving currents inside the superconductor. I will show it in a second. I will show it to you. But it turns out that sometimes when the superconductor is thin enough, it can actually lock magnetic field inside the material. And this is the origin of the demonstration you saw earlier in the video. The magnetic field lines are pinned inside the superconductor, and it brings all sorts of new exciting phenomena that, again, remember, in 20 years from now, we'll be able to demonstrate it in room temperature. That's the exciting thing. And here, for example, you can see how these flux lines, strands of magnetic fields.
Dr. Boaz Almog, I think you have shared this PPTs, but we are not, we are unable to observe that. We can't see the screen, your PPT.
Okay, so you don't see, you saw, okay. And now you see it better?
We can see your face only, but have you shared the screen for us or not? Any screen?
Okay.
Have you shared the PPT screen?
Yeah, I'm sharing it again. Let me.
But, we are unable to. Now we are
Okay.
able to see the screen. Okay.
Okay. So now you're able. Okay. Now do you see it okay now?
Yes, we can see the screen.
Okay.
Yes. Continue.
So I don't know if you saw the previous slides, but it doesn't matter. What matters is that here this is new science, right? New materials that are superconductor at room temperature. You see here a series of experiments. This was published in Nature 10 days ago, 2 weeks ago actually. So, and it's super exciting. And what I was showing you during a few minutes ago, it's a famous scanning electron microscope video that shows the flux tubes are stuck inside the material, and you can see the small circles that in a minute the illustration will disappear, and you'll see that how these round circles propagate. Oh, I think I need to, okay. Okay, now we'll see it better. So, okay. Sorry. Okay. So, it's just a video of an actual superconductor from above, and when we increase the magnetic field, strands of magnetic field enter the superconductor, and in this case, they get stuck in a very nice lattice, because the physicist who performed this, it's a Japanese physicist, engineered the superconductor so it have layers and layers of pinning centers. But I don't know if you saw the picture that this image that I took by scanning electron microscope of the superconductors that we produce in the university. But if not, have a look again, and you'll see that even in naturally occurring superconductor, this is a superconductor that we crystal grow in the lab. There's a lot of pinning centers, a lot of areas where the magnetic field lines can be stuck, and this stocking or flux spinning produces the effect that you saw in the video, and I will show you in a minute. Now, let me switch back. I want to switch back to the live view because I want to show you. Okay. Okay, great. So you saw in the video how a superconductor is being locked in a magnetic field, and you saw what a superconductor is, but it's all academic or theoretical. What we want to do is take the science from the lab and put it in the hands of students, of researchers in universities and colleges, and of course the public. So we developed a series of experiments that I'm going to show you some of them today, and feel free if you have questions. I don't know, but I'm open to any questions. But so okay, so first let me introduce what I'm working on. So what we did is we encapsulated a superconductor. I'm not important anymore. This is the superconductor. We took the superconducting layer, which is extremely thin, and we encapsulated it in a special thermal foam that keeps superconductor called for minutes. So now we can actually play with it and demonstrate certain things with it. So this is what we work with, okay? We dip it in liquid nitrogen and things start to become interesting. But before that, let's talk about magnets, right? So we know that here we have a regular, it's just a ring with several magnets inside. And, you know, and this is a track that we made in the lab with magnets. And you know that if I want to levitate magnets can either attract or expel. So if I'm taking, let me adjust the screen. Yeah. So if I take the regular magnet and I put it on this track, it's either attracted or it will be repelled, and it will just go sideways. So it doesn't want to levitate, of course. And if we want to achieve some sort of stable levitation, we need to support it from both sides, and then we get some sort of stable magnetic levitation. This is the principle on which maglev trains operate, right? You support it from all sides, and then you get frictionless motion. Okay, but now let's do a different thing. Let's take a superconductor. Instead of this magnet, let's throw it away. I threw it away. And then I'm going to take the superconductor. Let me take a superconductor that I've prepared in advance. Okay. Again, this is a superconductor that's been encapsulated in a plastic casing. And now before that, let's remove the support. Now, as you saw in the video, now we can put the superconductor on top of these magnets, and it is locked on this magnetic field. And now it can move without any friction, and we get stable magnetic levitation, which we couldn't have gotten just by using magnet. So it's a completely different effect. Now, this is a nice demo, but it's not enough. We want to do some experiments, and we want to measure things and see this phenomena in more details, and we can start exploring. For example, let me take a new superconductor. Sorry, I wanted to get another one, a warm superconductor. And again, the superconductor is on the bottom side. And when I put it in close proximity to magnet, I feel no effect, right? This is no effect whatsoever. And if I take a compass, regular compass, okay, let's see here. I see no effect, right? It's not magnetic at all. Now, what happens if I take the superconductor and I cool it with liquid nitrogen? Let's pour some more liquid nitrogen. Remember, this is the current superconductors who need liquid nitrogen, but hopefully 10, 20 years from now, we'll be able to do the same experiment at room temperature. And while it's cooling, let's say something about the origin of this phenomena and the fact that this phenomena is so unintuitive. The reason for that is that superconductivity, it's a quantum phenomena. Electrons inside a superconductor behave as quantum objects. And when you say quantum, what does it mean? It means that the energy is quantized, right? Energy cannot get any value that we want, the energy of the electrons, but it is quantized. And superconductors are engineered by nature or by man to have quantized energy levels, and the electrons can't move, can't change their energy because it's engineered so that the next available energy state is far, far away. So electrons remain at the same energy, which basically means they don't lose energy. That's superconducting. So returning to our experiment, I'm taking the same superconductor, and again, let's flip it over so the superconductor is from above, and again, there's nothing, okay? There's a lot of magnets, okay? So nothing. A little bit of, there are magnets from here, so it affects here, but almost nothing. But now let's do another thing. Let's lock the superconductor on these magnets. And what happens now? The superconductor pins the magnetic flux line, like in the presentation that you saw a few minutes ago, and currents start flowing inside the superconductor. And now when I remove the superconductor from the magnet, here, let's take this magnet far away, and let's take, you see, there is a lot of magnetic flux trapped inside. It's become a magnet, an electromagnet, right? Okay, so this is a demonstration of superconductivity, and currents will continue to flow inside until the material warms up. So this is a fantastic demonstration of flux spinning, and we can take this demonstration and do an actual experiment based on this demo. Let me show you. Let's do it full screen. So the idea is to do an experiment with this and to probe the actual pinning. So again, I'm taking a superconductor. I put it on a ring magnet. Then I remove the superconductor. And first, I'm probing the magnetic field of the magnet. So I'm just probing it to see what's the shape of the magnetic field. And because these are two rings and a single ring in the middle, you see double peak shape. Now I take the superconductor. Notice that I turn it upside down. So whatever I measure, it will be opposite inside, in sign, yes. And you see the same pattern, the same magnetic field that we saw in the magnet being trapped inside the superconductor. So this is an example of an experiment that we are doing with superconductors, and we do it in schools, universities, and so on. And another thing that we can do is probe the forces. Now, I don't know how long I have, but let me just briefly tell you about other experiments that we do. You can see in this video how we probe the magnetic forces between the superconductor and the magnet. So we have a magnet here sitting on a scale, and we take the superconductor and we put it in close proximity to the magnet, like this. And when you put it close by, what you see is a positive force, which means it's repelled by the superconductor, right? If I take the superconductor, let's, again, I'll be moving on and off from the presentation. Let's take the superconductor, and when I try to put it in close proximity to the magnet, it doesn't want to be here. So let's see, it will just, it will, see, it's repelled. It wants to go to the place where magnetic field is minimal, right? So this is the Meissner repulsion. It's repelled by the magnet, and magnetic field is expelled from the inside. But what happens when I force the superconductor into the magnet? At some point, the superconductor wants to stay at place. Let's do it on this one. So right now, when I'll try to take it away, it will attract. It will try to resist, right? What happens is gravity tries to pull it downwards, and the superconductor magnetic forces pull it upwards. Okay, so it resists any movement. And we can see this experiment. Again, I'm turning on my presentation. So these are the same magnet. I'm putting them in close proximity. You see the repulsion, but when the magnetic field line is pinned inside, you suddenly see that the magnetic forces change sign. And this is something you cannot see with magnets, right? Magnets are either attractive or repulsive. There's no changing in the behavior between magnets, and we saw that in this in the simple maglev demonstration that I showed you earlier. And one last thing I want to show you of what we're doing with students and with kids basically is, after we explain the basics of levitation and they understand that you just need to create, like in this demonstration, okay, what we did is we created a series of magnets all pointing to the same direction along the track, so the superconductor can follow the same magnetic field lines. There isn't any change along the track. So the only direction a superconductor can move without any friction is along the track. Okay? So you get frictionless motion. So we tell our students, build yourself. Okay, this is an example of a track that we built in the lab. It took us like 10 minutes. 10 minutes after you understand the concept, and then you can build whatever maglev motion you want. And you can explore the properties of magnetic levitation and frictionless motion. Now, I think I have a few more minutes, and the second thing I wanted to tell you is about another project that we did several years ago. And you know, we talked about electricity and superconductivity, but what about regular electricity and electric circuits and machines that you can build using electric circuits? And I noticed that it's quite difficult to teach kids about electric circuits because, you know, when you work with wires, you sometimes can't really see the circuits. If, for example, I'll take a regular circuit, it's quite complicated, right? You won't be able to see the circuit. So what we did, we designed a system which is based on building blocks, and it's based on basically regular building blocks which are Lego compatible, and in which you can build electric circuits. It's like what you see is what you get, but with building blocks. And with that, you can build circuits, you can build machines, you can explore basic mechanics and basic electronics and basic engineering. Let me show you again. So here is an example of how it works. You see, I'm building a circuit with the building blocks and connecting a motor here. Let me show you here. Let me stop here. Okay. There's a battery brick here, provides power. There is a switch here, and there is a light and a motor. And you can build whatever circuit, whatever machine you want to make. And suddenly the circuit is not a limit anymore. You're not limited by the fact that you want to have a circuit. You can build any mechanical, engineering, architectural structure you want, and you can incorporate the electronics inside. Let me show you what, this is my eldest kid. He took the Millennium Falcon, which is, a spacecraft by Lego, Star Wars, and he put electric circuits inside, and then it can be interactive. It can show action, light, movement. So anything you can think of, you can build with building blocks that conduct electricity. Here is another example. Again, this is my kid. He built it. It's like complex circuits that operate one another, and you get some sort of mechanical clock using just building blocks. So this is the sort of thing you can build using electrically conductive building blocks. And we want, again, the idea is to make the science, the engineering available to kids and to everyone who wants it, basically. And let me just end my talk here and ask you one simple question. And the question is, just imagine what happens if we combine these electrically conducting building blocks with superconductors. Remember, 10, 20 years from now, we'll have superconductors that conduct electricity without resistance at room temperature. Imagine we could build building blocks that are superconducting. Imagine what we could levitate, what we can build, machines. So that's on you guys, right? Research and create new materials, new stuff, new devices. And that's it for me. Thank you. And if you have any questions, I'm here.
Okay, thank you very much, Dr. Boaz, for your wonderful science experiment. And we have enjoyed a lot, all the experiments. And I have one question is that, what is the main science behind the flux spinning? How that is possible? That is flux spinning.
Yeah. So it's a good question. Okay. When we, at the end of the day, superconductivity is a phenomena that is preferable in terms of energy. It has a lower energy than the normal state. So the material wants to keep being superconductor. Now, whenever magnetic field lines enter the material, the superconductor is destroyed locally, right? You can understand it if you understand that superconductivity is being created by coupling of electrons. The two electrons being coupled by a mechanism, doesn't matter what the mechanism is, but two electrons are correlated between each other. And what a magnetic field does, it just breaks this correlation between electrons, and it kills the basic mechanism of superconductors. So superconductivity is preferable, and it is destroyed by magnetic field. But sometimes, and it happens all the time in most materials, again, in type 2 superconductors, there are areas that superconductivity is weaker. So it's easier, it's preferable energetically to let the magnetic field lines enter the material and then get stuck in these weak areas, grain boundaries. Remember the image that I showed you with a lot of grains, a lot of imperfections. These are the places where magnetic flux lines will be stuck. And the superconductor will do everything in its power meaning driving currents, and the currents produce a magnetic field, and the magnetic field interacts with the external field to apply forces. And by using these supercurrents and forces, it locks itself in the same position that the magnetic field lines were stuck. And then we get flux spinning. So it's just a minimal energy that produces force. That's it.
Okay. So, Dr. Boaz Almog, we have just shared this Google Meet on the YouTube, and once we will get the question and answer, and after some time, we will, in the behalf of you, I will give you the answers to the students. So, up to this point, I just keep the session, and thank you very much. In the end, I would like to give a vote of thanks uh, to the Dr. Boaz Almog on the behalf of Science Club AD Patel Institute of Technology, CVM University. I would like to take this opportunity to take eminent speaker Dr. Boaz Almog. Dear sir, your remarkable ideas, words, activities in the field of physics edified us. We are sure that this webinar would certainly galvanize our students, teachers, and professors through the scientific ideas progressively in the direction of the entrepreneurship. Once again, I express my gratification to the Dr. Boaz Almog for sparing his precious time with us. I like to thank our respected principal sir for his constant encouragement for this webinar. I would also like to thank Dr. Sudhir Vegar sir, and I like to thank our student team, especially Mit Suthar, for his constant support and execution for this event. And finally, I would like to thank all the active participants on this webinar. Thank you very much, Dr. Bose. And in future,
Thank
uh,
you.
I will approach for you for to prepare few projects for our institute and for your help and all the kind of support. I will once again I will contact you and hope I will have a proper idea from your side. So we have a wonderful project for our institute, and actually we are working on your project, on your idea, and in a future we will have the same project for our institute where many students can interact with us, and through this we can give some encouragement to the students and how the engineering science can be we can take outside the laboratory in terms of entrepreneurship. Thank you very much, Dr. Bose.
Thank you.
Okay.
Thank
Thank
you.
you very much. Thank you very much, Bose. Goodbye.